Okay. Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. This is the second lecture of EE 4684. Basically, this is the plan for this lecture. We're going to start with some description of images as arrays. And basically, I thought instead of downloading some images from the internet, I think we should just rely on the images that are present in Matlab. There are some built-in images that are present in Matlab. So basically, there are some tools that I'm going to show you now. And just get some of us working on a different image. So basically, what I'm going to do now of these images. The path. This is what I have. This is the Matlab directory I have. Just go in and go to toolboxes, and then toolbox. After that, see images. Images is the image. Can you see what I have?
No.
I'll enable the screen. That. Okay. So basically, this is inside Matlab. So, like this. Directory. You have your version here. Go inside and then look. Go inside. Images are is in the image. And then inside you will find a directory called imdata, image data. Okay. When you go inside, you will find so many images, so many different disciplines. Images like the this is a cell image. What else? This is a histogram. Microscope, you see something like this. There are several images. These are like samples. And basically, they are all in the path of Matlab. So basically, if I go to Matlab, let's get started. Basically, if you want to read an image, all you have to do is just say, this is your variable. If you have this variable, let me clear all thing here, clear. Of image name. Between just choose one of these images. Let's start. Cell images looks like a black and white image or a gray. Get started with that. So basically, I'll just type. This is cell dot. Let me get the exact. Is one. Images are TIF. Images are .gpg. Some images PNG. So different images. It's very simple. You just write the name of the file, and basically, file it will know how to read it. Okay. So basically, I didn't put the path. Basically, I'm standing. You read, and basically, it gets you the image in an array like that looks like this. Basically, image is a 159 by 191 unsigned integer array. So basically, an image is an array. Basically, it's just a collection of points that are basically formed as a matrix. Each point in the matrix, each entry. Okay. So basically, just
Yeah.
we read an image, and basically, in order for us to have image, and you so basically you read the image, okay? So this is one sample image. Let's try with another image that has color, just to see the difference between color images and black and white images. Pick the histology image that looks like this. It's histane.png. Here again, let's just say image of histane dot, I think PNG or GPG. It's PNG. Image here, you look at the difference between these two. The first one is black and white, it is grayscale. So basically it has only 159 by 1921. So each point in the image has only 1 byte, basically. You have 3 bytes. Green and blue, basically components. You will have an array that is x times y times 3. And this, if you take only one of these 3 bytes, you will get something that looks black and white. I'll show you that in a minute. But actually, if you just take this image here, basically just say again, image show of image 2. You'll see the image in color. Pick only one of these. Let me basically just try to see image show of image 2 of all and 1. This is the first color component, okay? The problem usually is that for any image display routine here, it expects you to have a 2-dimensional array or a 3-dimensional array with the last entry as 3. Let's see if we try this here. Actually, it worked. Actually, I was surprised. But actually, it basically showed you something that looks black and white, because this is one component. Assume that basically you have grayscale. Let's try the second. The intensities of they don't look exactly the same. Brighter than the other ones. Okay, so basically, if you just display it as image 2, it will display it as a color image and use the last array dimension as the color dimension. And basically, it starts from there and basically displays the image in color. If you choose only one of these, then it would display it in grayscale. Okay? Everything's clear till now? Any questions?
Yeah. Okay.
Okay. We actually we're losing people. We actually we don't have Reno now. We don't have Anas now. Anas has no connection for some reason. Okay, I have to continue, but I'm not sure why actually. Okay, there are other ways of displaying the image, like for example, image SC. Okay, image or image SC. Basically, the difference between the two is that image displays the image assuming that you have basically the colors from 0 to 255. If you are beyond that, if you are much larger than that, in some images that you will see, actually, the images may extend beyond that. Sometimes the image has negative numbers. So basically, image doesn't account for that, and it's very difficult for it to work with them. For image SC, it's basically a scaled version of image. So it scales the range of the image to the range of the display between 0 and 255. So image SC, if I say, just say image SC of image 2, or image, just to see it, okay? You'll see something that looks like this. Actually, for image SC, it displays with what's called a color map. The color map here is not grayscale. In order for me to get it as grayscale, I have to say color map gray. So that it knows that what I'm displaying is a grayscale image. Okay. So basically, it will if I change the color map to gray, it will look like this. So basically, you can either use image show, or you can use image SC with color map gray if you want to display a grayscale image. Okay, if you want to display something that like the image 2, like it's a color image already, so just say that image SC of image 2, and it should be fine. You will see it correctly without all. So basically, the images are arrays. If you have a grayscale image, it will look like a 2-dimensional array. If you have a colored image, it will look like a 3-dimensional array with the last dimension as 3, representing the 3 basic colors: red, green, blue. Okay. Okay. So basically, we'll try now to basically try to look at the images themselves. So let's get back to the. We already did that. We would like to look first at image magnification. Okay, how we do image magnification. Okay, first of all, let's basically imagine how the image looks like. So basically, we have the image as an array, and basically, as long as it's an array, then it would look like this. Basically, if you have basically different columns of this array, you look like this. Okay, different rows. So basically, this is a very basic image, very simple image. Okay, let's assume that we're going to have basically the points that we already have are basically these points. Sorry. Okay. These are the points that we have in the array, basically.
So it's like three size array, doesn't it?
Yes, basically you have the image, that the entries in the image, the array itself basically will be these points. So basically you have numbers like, for example, 200, 150, 100, for example, and for example 129, 211, 111, for example 75, 80, 95, for example. Okay, so basically you have the image that looks like this. Basically it's an array that looks like this. What happens if I wanted to take this and basically get an X2 version of it? Meaning that basically I have to magnify it. Okay, magnify it by a factor of 2. What would happen? This means that instead of just having these rows and columns, we're going to have actually more rows and columns. For example, between each 2 columns, we're going to have another column, another new column. And here we need to have another new column. we have to have here one new row. Here, the same thing. Okay. Okay. How about these points? A point that looks like this here, the one in the middle here. How can we compute that? Okay. How can we compute this one here? How can we compute this one here? How can we compute the other points that are in the middle that don't have them? Okay. I have so many points that I don't have, because basically if I started with an image that has n1 by n2 rows, now after I magnify by a factor of 2, I'm going to have 2n1 times 2n2, which is basically 4 times the original size. So basically I'm missing number of missing points that I need to have 3n1 and 2, which is a large number actually. How can I estimate these points? Okay, does anybody know how to do that? How can you estimate the points in the middle here? For example, this point here, how can I estimate this? Basically, there is a technique called, in mathematics, called interpolation. You may have heard of it before in mathematics, in the context of one-dimensional arrays. Like, for example, if I have a curve, basically, I have, for example, if I have x and y, let me draw it properly. If I have x and y axes, basically this is x and this is y. I have the value of x, or value of y at x here. I have this point here, and I have the value here. So let me just put it as a different symbol, because actually this might be confusing. Let's just have a point here and a point here. Okay, I have this one here, I have this one here. So basically this one basically is corresponds to x1, and this corresponds to x2, and this is y1, and this is y2. Okay, how about if I wanted to basically estimate the value of this function at another point here, x3? What can I do? Okay, so I need to estimate where exactly here will be y3. What can I do? Basically, the interpolation assumes that there is a certain curve that passes through these points and tries to estimate this curve, and then from this curve it can actually estimate any point in the curve. So for example, one very simple example, okay? I'll assume that the easiest curve I can assume is that basically I have a linear curve. If I have a linear curve between these 2 points, how can I estimate any point in the middle? Obviously, if you have a linear curve that looks like this, so basically the ratio between x3, this is x3, okay? This is basically x3, this point in the middle, basically. y3 here, if I can just draw it as a triangle here. Basically, if you have this x1, this is x2, and this is basically y1 and y2. The ratio between this and this will be exactly the ratio between this, if I have this y, this is the value of y, to this whole thing. You have like a similar triangles. So basically what you're going to have is a very simple way of estimating the point in the middle. For example, if I look at a point that is basically x3 equal to x1 plus x2 over 2. So basically a point exactly in the middle. What's going to happen, what you're going to see that is y3 will be exactly equal to y1 plus y2 over 2. So basically it's going to be in the middle between y1 and y2. So this is a very simple way of doing this. You can actually do this also to the image. Instead of having a one dimension, this is 1D, okay? You can actually very easily convert it to 2D problem or a 2D solution. So instead of doing that for basically y as a function of x, now you have a function of x1 and x2, because basically you have two dimensions now. You have rows and columns. So basically you can do that very easily. This is a very effective interpolation technique that is called basically, this is linear interpolation. And in most cases, actually, this is more than enough. This can be very sufficient for the basic problems. If you want to have a higher quality, if you look at the fine details, then you want to go a little bit higher. So basically, you want to instead of just fitting the points here in the middle between these 2 points, the two given points, instead of fitting them into a linear curve, you can have a higher order curve. So basically, instead of having linear interpolation, there is a new technique or another technique that is a little bit more sophisticated, basically, that is called cubic interpolation. If you take this example here, what you say in this example is that basically y is equal to ax plus b. Basically, you estimate a curve that looks like this. If you want to estimate a linear curve, I have two parameters, basically. I have A, I have B. If I have A and B, then I can estimate this function for any x. What I do here is that I estimate A and B from the two given points. I have two unknowns and I have two pieces of information. So basically, I can estimate A and B. But the problem with that is sometimes the curve is not basically, it cannot sufficiently be estimated as a linear curve. For example, let me give you a very basic example. If I have a sinusoidal signal, for example, okay? Assume that you have a sinusoidal signal, okay? You have a sinusoidal signal that looks like this, okay? And basically you have a point here and a point there, okay? And you want to estimate the point in the middle here. If you assume that this will be done or sufficiently be estimated using linear interpolation, then the curve would look like this. And you would estimate your point in the middle here instead of here. If you use a cubic interpolation, then assume that y is equal to a x to the power 3, z b x to the power 2, z c x to the power 1 plus d. So basically you have four parameters. You estimated or basically put your curve as a much higher polynomial. So basically it can actually accommodate something that looks like this. But in this case, you have four unknowns. You will need to have four pieces of information. So basically, instead of having only 2 points, you have to have actually 4 points for you to be able to fit that curve properly. And then you will estimate this point much closer to the actual point than what you estimated from linear interpolation. This is exactly the same for images, exactly the same. But actually, as I was saying, you have two dimensions. So for example, if you want to talk about the linear interpolation would look like the curve for it for the two-dimensional case would be like y is equal to ax1 plus or a1 x1 plus a2 x2 plus b1 plus b2, because you have two dimensions now, x1 and x2. And basically you have 2 dimensions basically for the image, and basically as long as you have 2 dimensions, then the estimate here, this is the intensity, will be a function of both dimensions. So basically you can estimate these parameters and basically estimate the value in the middle based on that. There is another technique for interpolation that is much worse than these two. These two are really good, okay, because actually they try to understand the trend of the image and estimate the missing points based on that trend. Okay, there is another technique called nearest neighbor interpolation. Right, we can green. Nearest neighbor. So basically, what it does for the nearest neighbor, if I look at the image that I was talking about, let's just talk about the example of just I have 2 points here, it's just 4 points. Okay. And if you want to estimate a point here, you would estimate it direct to be exactly this point. If you were here, then you estimate it as this point. If you're here, you estimate it at this point. If you are in the middle, you estimate it at any one of them. Okay, so basically you estimate the point. Y is exactly equal to nearest neighbor, nearest point. Okay, let's see what the impact of each one of these techniques on the actual quality of the enlarged image. So basically, let's take the image that we just read and basically try to magnify it and see. Okay, let me just draw it first. Let's just get the first one. Let's just show the first one. This is the cell image that we talked about. And actually, it's a very small image. So basically, it appears like that on the screen. But actually, if you magnify it here, basically, the usual behavior of Windows, if you're trying to look at an image using Windows image viewer or in Matlab, a figure that looks like this, and try to magnify it, the default behavior is to use the nearest neighbor. So let's try to magnify this and see. See? Basically, we try to magnify it now. See what happens? What happened here? What do you see? Basically, because of the nearest neighbor behavior, you will find blocks. You will find that basically what happens is that each point and its neighbors will be exactly the same. So it will look like as if I magnified the pixel size. So instead of having smaller pixels, as I would expect from a larger image, I have larger pixels. It's exactly the number of pixels here. So each one of these squares here is a pixel. The magnification using the nearest neighbor technique is just a way of displaying the image with larger pixels, which is really very poor. If you see something like this, it's extremely poor. You can't really see much. If you magnify it here, you can't see what's going on here. You don't really see much. Let's see what happens when we try to do it or to do this magnification using one of the other techniques, linear interpolation or cubic interpolation. We're not going to do the estimation I was talking about by hand. There are functions that do that in Matlab, but we need to just go over the theory of how they are estimated, because actually you need to understand what's going on. You need to understand the function that you're using. So basically, there's a function in Matlab that is called image resize. Okay, help. I am resize. So basically, if you look at it, maybe you should look at the help. Look better, probably. It's right there. So basically, you just put the image and the scale, and that's it. Okay. You can also say, instead of saying that, you can actually say that I want to magnify A to B, this number of rows and this number of columns. The important thing that you should worry about, or basically related to what we're talking about now, is the methods. let's see the method here. You have nearest, you have bilinear, and you have bicubic. Linear interpolation is for one dimension. Bi means two. So basically bilinear is linear interpolation applied in 2 dimensions, in x and y. Bicubic is also a cubic interpolation applied in the 2 dimensions, the horizontal and the vertical. It's exactly the same. So basically, when we use the image interpolation, we just say the method that we're going to use, and basically this will show us, or basically tells the function to basically estimate the missing points using this technique. So what we're going to do is basically we'll go to I now. Basically, we're going to read the image. Just start with image, image read. We start with cell.tif, which is the one that we just read. And then we say that image 1 will be image resize. Let's factor. Yes, go ahead.
There is a function used to magnify, rearranging or resize the 3D image in the Matlab, or only for 2D? For 2D?
Actually, it's exactly the same. So basically, if you have 3D, you can actually do tricubic. Basically, you basically try the same thing in the 3 dimensions. But basically, for us, we have to actually look at it in the 2 dimensions. But actually, if you want to generalize it, you can still do that. Okay, and basically, you can either do it. I don't think there is a function in Matlab that does that for 3D, but you can actually use iterated 3 dimensions. So basically, you just use the images, because actually the volume is just a set of images. So you magnify each of them in the x and y dimensions, and then you basically look at the images in the z direction and basically magnify in the z direction as well. Okay? But this is a very interesting question, by the way. So image resize of this image that we just talked about, okay? And let's put the factor. Let's just say magnification factor equal to what? Let's just say 2, okay, for now. Or let's just put it up a little bit larger so that we can see the effect. Image resize and this magnification factor, and basically we put the method that we just showed. Basically, it's from the help that we just saw now. Okay. Basically, we're looking at the help here. Basically, you have either nearest or bilinear or bicubic. So we're gonna try the 3 of them. So basically, I'm gonna repeat that for, sorry. And I'm gonna put here bilinear, and I'll put here bicubic. And basically, I'll call this image 2 and this image 3. And then I'm going to display the 3 images. Okay, so I'll just say figure of 1, just to make the figure pop whenever I start the execution. And now I want to have the 3 images side by side. So I'll have an array of images or array of figures inside figure 1 that is 1 by 3, 1 row and 3 columns. And I'm going to start with the first position. Okay, and then I'm going to use image show image 1. Display the first one. I'm going to repeat that. Sorry. For position 2 here and position 3 here. And this is image 2, image 3. Let's see what happened here. Okay, it's untitled. Let's call it lecture 2. Okay. Okay, so this is what we have now. Do you see any difference between these images? Actually, it's very difficult to see the difference because actually they are very small. They are displayed at very small, size. So basically, I'm gonna zoom in a little bit. Can you see the pixelation here? It's present here.
Yes.
Okay, let's see this one here. Let's just zoom on the same exact location. This is the bilinear interpolation. How do you like that? Much better, right?
Much better.
Let's see that here. This is a bicubic. Actually,
Bicubic is more.
Yes. So basically, as you see here, it's very different. Okay, and in some cases, in many images, actually, many scenarios, imaging scenarios, the image size that comes out is really small. If you display it in just nearest neighbor format, you're gonna lose a lot of information. You're not gonna basically show the doctor what he's supposed to be basically seeing in the image. Okay, so basically interpolation is very important. You have to select the interpolation technique that would allow the quality of the image to be maintained when you magnify the image. Otherwise, you're not going to be able to see the quality of the actual image. Okay, maybe you can see also that this part here, for example, this is still okay, but actually it's not as good here. It's extremely pure. It's extremely poor. If you compare this one to this one, it's a big difference. Okay. So this is it clear now how the technique of interpolation makes the magnification of an image much different, much more different when you try different techniques?
Yes, thank you. No, is there any condition that when we use the nearest neighbor, or when we use the
actually, if you're trying to magnify a medical image, you should basically use bicubic, at least not less than bilinear. Okay, for common image display functions or basically softwares for regular images, they really don't care. So basically, they display it in nearest neighbor. They don't really assume that you need to get into that much detail. Okay, but for medical images, because first of all, the size of medical images is much smaller than the current digital imaging, basically digital photography. In other words, digital photography sizes now are really huge. So if you look at any common mobile phone, you will have, it's easy, you can get an 8 megabyte camera without any problem. For medical images, it's really difficult to get that high resolution. So basically, when you try to manipulate or display a medical image, you have to take care of that. You have to be careful not to use the crude nearest neighbor interpolation, and you have to use basically something that is more elaborate, like the cubic interpolation. And as you see here from Matlab, it's very easy. It's just a matter of choosing which technique to use. Okay, let's try one other experiment. Basically, because actually I have to break for the prayer in about 15 minutes, I'm going to show exactly the same example here. Instead of having this black and white image, I'm going to use the color image that we saw. Okay, so basically I'm going to use the histology image. I think it was histane.pmg, I think so. So basically, let's see if it makes any difference. Okay, if I use a colored image, would the pixelation be different? Let's see. Okay. Okay, the image looks okay, right? If you magnify, see the same thing here. Pixelation, right? Let's try to magnify it here. This is exactly the same location. Okay, see how the difference between these two? Do you appreciate the quality difference between these two images, all of you, or you don't see that?
Yeah, we can see.
Basically, all three images are coming from exactly the same image. See, for example, this one here, this part here, this line here, looks very nice. Here looks a little bit fuzzy, but actually here it's gone. It's basically you don't really see what's going on. Okay, so basically it's exactly the same problem in in color images as it is in black and white images. Okay, and the larger you magnify, the larger the problem becomes more prominent. The more the problem becomes more visible to the user. So basically, if the doctor is trying to look at an image that looks like this, actually it's very difficult to basically see a lot of the details. See here, it's very nice. Okay, you see a lot of things that don't really appear here at all. Okay, you see lines, you see things, but basically you don't really see them because of the pixelation here. You don't really see the outline here of the image. Sometimes when you do something like this, by the way, some people call it, if you have an image that is constructed with such pixelation, sometimes they call it an aliased image. We heard the aliasing before in the context of sampling, but actually here it's very similar to that. It's a problem here in the image because basically the sampling is too coarse. Okay, whenever you have a coarse sampling, it means that basically each one of these pixels, the large pixel, represents a very large area. Instead of here, basically if you look at this here, the same part here, you see it starts to see pixelation here. But actually if you look at this one here, you don't really see pixelations before a little bit of magnification than that. But actually, whenever you start seeing pixelations like this, you realize that you have a problem of sampling. The samples here are too large, or basically the spacing between the sample is too large. You should have had more points in your image so that you can actually see the details of the image that you have in each one of these images. Okay, so basically, do you know now how to read an image from this code? You know how to read an image. Basically, these images are present in the data, the present data in Matlab. These are basically sample images that are present in Matlab. You can actually try images from different fields. You can try the cameraman, you can try, these are cell images. You can try something like a hand. You can try something that looks like a spine here, like MRI. Can have actually some of the histology images are still here also. So basically you can try these techniques in each one of these images and see if you see a difference. We focus on medical imaging because actually this is our field, but actually it's exactly the same for each one of these different images. So basically what I did here was to upload one of these, basically read one of these. As I told you, if you're using one of the images that are built in Matlab, then Matlab knows where it is. Okay, so basically, if you just put the name of the image, it will basically go and basically read it from the image data directory that is present within Matlab. Okay, these are two sample images. This is a black and white image. This is a colored image just for a demonstration. All we did here was to choose a certain magnification and basically use nearest neighbor interpolation, by linear interpolation, by cubic interpolation, and basically compare these two in a figure like this and basically comment on it. What we just did was one part of the research problem one. You will be asked to basically read any medical image. You can actually choose the medical image of your choice and basically try to magnify it with a certain magnification that I will give you, and basically give me your opinion. What you basically should do is basically get the images, get the outcome from here, and basically document that and give me your comment. Which one is better and why? Usually you're talking about better in terms of lack of pixelation, lack of these large pixels in the image, okay? And basically can talk about also some of the details in the image. For example, if you look at the details here, sometimes the details, if you look at this line here, it looks a little sharper here. So basically, sometimes it's kind of, it might be a little bit subjective, but actually I need to hear your opinion, okay? If you say, for example, in some images that you see that bilinear interpolation is better for a certain reason, it's fine. but actually you have to give me your opinion on this. Okay? Do you have any questions so far? I saw that the other people are now with us. Um, do you have any problems following the lecture after you came late? I'm talking to Abdullah and Muhammad. Do you have any problem following the lecture? Do you have any problem following the lecture?
شغال عندي تمام بس اظن محمد عنده مشكله اظن.
Okay. You're having problems with Blackboard or with the internet?
عندي مشكلة في الإنترنت.
Okay, is it fine now? Is it okay now?
Okay.
Okay. So, okay, we decided that we're going to take a break at 7. Would that be okay, or would you like to break now and come back after just break, or wait until 7? We can either break now or wait until 7, because actually if we're going to break at 7, then we're going to start another topic now, another different thing. So instead of
Can
talking
take
about
the break now.
communication, okay, so let's meet again in about about 15 minutes. Would that be sufficient, like 7:05? Okay, so 7:05. Okay, we're gonna start again at 7:05. Okay.
إن شاء الله.
Okay. Assalamu alaikum.
Walaikum salam.
Are you all back?
Yes, doctor.
Okay. So now we're going to talk about image rotation, and it's actually very similar to the problem of image magnification, which is going to be surprising to you. Let's try to draw the geometry of image rotation. So basically, if I have an image like what we draw, what we actually had before, basically I have columns. Okay, like this. Okay, and basically assume that these are also exactly the rows. Okay, so basically these points here are the original points in the image. Okay, let's assume that we would like to have a rotated version of this image. So basically the rotated version would look like, for example, this would go here, like it's going to be like this. Okay, and basically here the lines would look like this. Okay, so basically now you have a very different way of displaying the image. So basically instead of having the you'd like to have at least the new image coordinates that you have for the rotated image. For example, if you have a rotation by an angle of 60 degrees, for example, then what you're going to have is for each one of these points, basically you moved into another point that looks like this here, okay? And basically, after you do that, you need to estimate the new matrix after you do this. So for example, basically, this is the point that you have already, okay? These are the points here, the vertices here are the points that you already have. In order for you to display the image, basically these points like that here, let me just point out a few points that we talk about. This point right there. This point right there. Okay. Basically, this point is not on a coordinate system. Basically, this point here, the new coordinates of this point here are nowhere near integers. For example, if you have a matrix, and this matrix is, for example, 100 by 100. Okay, you have an entry of 1 and 1. You have an entry of 50 and 50, or whatever, any integer and any integer. But you don't have any entries of like 10.4 or 10.3 and 20.4. So basically you have a problem because actually the actual point that you already have are now on a non-integer coordinates, basically. You have to find a way of estimating the points on the matrix, like if you have 10.3 and 20.4, you would like to have 10 and 20, and you'd like to have 11 and 20, and so on. So basically, given these points right there, okay, this point here, okay, you would like to know the new points or the new coordinates or basically the other points here you'd like to estimate the blue ones from the purple ones. How can you do that? Basically, let's start with a particular example for this point right there. Sorry. Let's just take one particular example, this point right there. You have basically, you would like to estimate at this point from this, this, and this. You have to actually estimate this point from the points around it. This looks like a very similar problem to the problem that we saw in magnification. This is an interpolation problem. Interpolation means that you have a curve, okay? Basically, if I have X and Y, or I have a table, let's just put it in a table. I have a table of X values and Y values. Okay, you have here X value, and you have here Y value. You have at X equals to 1, you have the value of Y. You have X equals to 2, you have the value of Y. You would like to estimate the value of the point in the middle here. Okay, so basically this is an interpolation problem. Interpolation, you have point from here, point from there, you have a point in the middle that you'd like to know. There is another problem, very similar problem in other than interpolation. There's a problem called extrapolation. Extrapolation means that you have a point here, a point there, you would like to know a point outside of both points. Okay, extrapolation is used in the basic some techniques for prediction, or if you have, for example, the stock market, you'd like to predict where it's going, something like that. So basically, extrapolation is basically you're trying to get more data that are not between data that you have. Okay, so basically, this is an interpolation problem, and as long as it's an interpolation problem, then you would expect it to also have the same problems that you saw in image magnification. It depends on the technique that you use for interpolation to produce results. Here, actually, you will see that regardless of the technique, you will have problems, because basically the kind of rotation, the kind of irregular positioning of the new points that you'd like to estimate will make the technique actually very difficult to work. Let me give you an example. In order for us to see a particular example that shows exactly the problems of rotation, we'll basically try something that has very clear edges so that you see what happens when rotation occurs. And basically, when you see this particular example, you can basically extrapolate, if you want to say that, use the same term that we talked about, extrapolate what would happen if you rotate a medical image. Okay, so we'll go back to Matlab here. So basically, let's just put here some comments just for you to understand. This is the magnification part, and this other part here will be the rotation part. Okay. We're going to start with exactly the same things that we saw here. Okay, let's just copy this whole code. Okay, we're going to read an image, but instead of using image resize, there is another function in Matlab that is called image rotate. Well, image rotate. And basically, when you look at the image rotate, you're going to find the same exact options that you see here: nearest, bilinear, cubic. So basically, it's a angle method. So A is the image, angle is the degrees that the image will be rotated by, and the method basically use one of these techniques. Okay. There are some other options here that you might want to consider. Basically, because when you rotate, let me just show it to you here, because you actually need to understand it. Basically, if I have an image that looks like this, like just, just a square like this. Okay. Basically, if you rotate this, see here, sorry, by an angle of, for example, let's say 60 degrees, for example, or whatever, 45 degrees. Okay. The shape of this image after rotation by 45 degrees would look like this, basically. Roughly, okay? Okay, because actually rotated by 45 degrees. So basically, you will see that some parts of the image will actually, basically, the new image will lie in a much larger frame than the old image. So there are two options here in Matlab. You have crop or you have loose. Crop means that if you have an image that has this particular size, the rotation or the rotated version of this particular image will have exactly the same size. So any parts here that are outside the original image will be removed or cropped. Cropping means that you're removing some parts of the image. So basically, these will not show. Okay, if you use loose, then basically you're going to see that the image will be basically much larger or significantly larger depending on the angle. So the outcome of the rotation will differ by the angle. Okay, so for example, if you rotate by 45 degrees, it's going to be larger. If you rotate by 90 degrees, what's going to happen? Basically, it's going to be just rotation. So basically, it's going to be exactly the same size. Because actually, it's going to be best just this will come here, and this will come here, and this will come here, but actually the same size will be exactly the same. If you rotate by 180 degrees, it's going to be also the same. So basically, if you use any angle other than multiples of 90, you will have a larger image. Okay, so let's try to see what's happened here. So basically, let's just try to use image rotation, image rotate, each one of these. And basically, this is the angle. Let's just call it angle, so that we can put different angles and select it from here. We're going to try it also for color image and black and white image. So let's just say 60 degrees. Okay. And here we use nearest first, bilinear second, and bicubic third. Okay. Let's have another figure so that we can have all the results showing. Let's start with the black and white image. It's going to display in figure 2. Okay, see now? How do you like the image now? Okay, it's rotated, right? But actually, if you look at it, see here how it looks like? It's a little bit better. A little bit better, but actually these two are close to each other, but actually this is definitely much worse. See here the pixelations here, see how the sharp pixelations that it shows here. Here, if you look at the quality of these images, you will see a big difference between the three. You have this quality here is not very acceptable actually. You can't see much here, but it's a higher quality. But if you look at it a little bit, you'll find that it has problems. It's not really without problems. Okay, basically in rotation, whenever you rotate an image, you lose some quality of the image. Okay, there is no way you don't lose quality because of the rotation. Actually, the interpolation that happens might not exactly reflect what's going on in the image. So basically, whenever you have rotation, you're likely to end up with quality loss. So if you are dealing with a medical image, and the doctor tells you that is it okay if I look at the image rotated by 45 degrees? The answer should be no. Actually, you should look at it the way it is, because actually when you do the rotation, the quality of the resultant image will be a little bit less than the original image. Okay? Let me try this again on the color image, and then I'm going to try it on a simulated image. Okay, this is the first one. Okay. Please try to do exactly the same as what I'm doing right now after the lecture. So basically start with the code. Basically, I'm going to post this code to you on Blackboard. And basically, what you have to do is basically try to maybe change the images, change the magnification, change the rotation angle, and basically try to get some experience manipulating the images, okay? And if you have any problems, just ask me, okay? So basically, this is the rotated version here, okay? Let's look at this. When we magnify, same thing here. Same thing here. This is definitely poor. Actually, see here, the outline here looks really poor. Here, it's not perfect, but definitely better than this one here. Here, actually, if you look at it, it's a little bit better, but actually, it's very difficult to distinguish the difference between the bilinear and bicubic. But actually, they are both better than the nearest neighbor interpolation. You notice here that you see pixelations very early on. So basically, it's not a good thing. Okay. So whenever you rotate an image, you should expect to have some quality loss. In order for me to show it to you in a little bit clearer way, I'm not going to use any one of these images. I'm going to create my own image. Okay. So I'm going to create an image that looks like zeros of, for example, 256. Okay. Or 128, doesn't matter. And then this is zeros. Basically, this is an image of zeros. Okay. I would like to have a white rectangle in the middle of this image. So basically, what I'm going to do is basically this is an array. I'm just going to set the values in the middle rectangle to be like 100. Okay. So the middle of 128 is 64. So basically, it's going to start from say 33 to 64 plus to 95, okay? So we're gonna repeat that here. It's not critical to be exactly like that, but let's try it this way. Okay, let's see it. Okay, see here? This is a rectangle. Okay, let me show you the rectangle first, how it looks like. Okay, just to make it a little bit clearer, and I'm going to have here four figures. Okay, and then the first one, I'm going to display the original image, so that you see that we don't have any of these jagged edges in the original image. I'm sorry. What? Okay, I overdrew. Should have changed that. Okay. See, this is the original image. Magnified the way you like is going to be exactly the same. You don't really see any problems with the edges are very sharp. Okay, this is the original image. Here, after I rotated that image, see how the edge becomes? Okay, it's like a stamp. Okay, like the stamp edge. So basically, it doesn't look like a very high quality interface. Imagine that if you have an interface between two tissue types in a medical image, okay? And if you rotate the image, then this interface will look something like this. So basically, you're not going to be able to distinguish exactly where that interface is going. Okay, and this is a big problem. Okay, so you're going to lose quality here. Let's see here how it looks like. Is it better? I don't know. It's not really much better, to be honest. So you're going to have problems in each one of these techniques. This is bilinear. This is bicubic. As you see here, you might see that these a little bit, they are a little bit smaller variation than this, but actually they are all having variations. So regardless of the type of interpolation, you should of course use bicubic interpolation, but actually in each one of the different types, you expect to have problems because of this the interpolation exactly render the same exact points that are already in the original image. One more thing, this is actually a very known problem in high quality imaging, is basically called vector quantization. It's basically if you're trying to draw a line at an angle on a screen. The screen actually looks like a matrix. Basically it's a matrix. It has certain points, and if you're trying to make a line go, basically it's very similar to something like this, basically like the one we were talking about. If you're trying to draw a line like this on a screen that has points like this, square points like this, you will have a problem assigning the value of this line to which pixel. It's going to be a problem, really. So basically, this is, unless you have a very high resolution screen, you're not going to be able to render any diagonal line in a perfect way. You're not going to be able to see it basically like what you see it here. You're not going to be able to see it very clean with very clean edges that look like this. So whenever you have an interface at an angle, be careful that the screen or the display, the way you display the image, will affect the quality or the definition of this line. Is that clear?
Yes, sir.
Okay. So now we saw that we have techniques for magnification of an image, or basically rotation of an image, and they are both dependent on interpolation. The basic background of each one of them is interpolation. So basically, the thing that the conclusion that we can come up with from both is that basically the technique of interpolation may affect the quality of the image. You need to use a higher order interpolation technique like the bicubic interpolation, so that you can get high quality images. Okay. So let's go back to the plan that we had for this lecture. We already did that. Images versus arrays, images as an arrays. Grayscale versus color images. We said that color images are two-dimensional plus a third dimension of 3 to represent red, green, and blue. We talked about the geometry of image magnification. It's an interpolation problem. We need to estimate points in the middle of the points that we already have. We talked about interpolation techniques like bilinear, first of all, nearest neighbor, bilinear, and bicubic. We show example magnification for grayscale and color images. We talked about the geometry of image rotation, and also we found that it's an interpolation problem as well. And we saw examples of the interpolation used, or basically how to do image rotation using the different interpolation techniques. Okay. The last thing we're going to talk about today, which is one thing that we talked about last time, I would like to repeat it again. Basically, when we're using actual images. So basically, we're going to talk about these two topics. the quantization, which are very similar to what we talked about last time. We're going to apply them to the images that we have right now. We're going to apply them to grayscale image and a color image. Okay, it's just an example. Okay, I would like you to basically investigate some more data, some more images, different images from the Matlab resources, or you can download images from the internet for CT, for MRI, for whatever, and basically try everything that we talked about here in these different techniques. Let's go back to the end of the talk about quantization again. So if you talk about quantization, basically in different imaging modalities, the range of the images, the range of values of the images vary a lot. Basically, if you want to talk about the images that we are displaying on computers or personal computers, basically we assume that from the images have levels from 0 to 255. Okay, this is for grayscale, black and white. Okay, if you have color, then you will have 3 of them. Okay, you have red, green, blue. Okay, from 0 to 255. Okay, this is the usual display range of a personal computer, or basically the regular monitors that we see attached to computers. The problem is, for example, for CT, we're going to talk about CT in probably next lecture or so, when we talk about DICOM images. The range of these CT images is from -1000 to basically maybe 2,000 or 3,000. Okay, it's very different. Okay, if you talk about MRI, actually MRI depends on the way you acquire the images, as we're going to see. Actually, this is one of the things that we're going to do practically. Sometimes the images, the whole image, will have a maximum value. First of all, the images might be negative. It might start from negative numbers to positive numbers. Okay, but the range might be like 10 to the -6. The maximum will be 10 to the -6. Okay, meaning that it's very difficult if you just take the image from an MRI system and just display it the way it is without scaling. This would be a problem. Okay, because you're not going to be able to see anything. Okay, so quantization tries to take whatever range. If you have an image range from minimum to maximum, okay, this is the range of the image. Okay, you want to take this range and basically try to divide it into levels. Okay, and the number of levels is the quantization of this particular range. Okay, so basically you assume when you have an image from minimum to maximum, you assume that this is 0, and this is, for example, L is the maximum number of levels. The maximum will be L. Okay, so regardless of the minimum or the maximum of the image, you're going to end up with the image that has L levels. This L levels can be, for example, 256. Okay, let's just say L -1 so that we have L levels. Okay, from 0 to L -1 is L levels. Okay, this is what we say when we say that the quantization is, for example, 16 bits. It means that you have 2 to the power 16 levels. Okay, and this is basically, this is if you like to listen to internet radio, you have different channels, and they say that the sampling rate is so and the quantization is so. So basically they say that this channel is 16 bits or this channel is 32 bits. Also, if you try to record your voice or something like that, basically you have different options. You can basically, if you have 16 bits, it's like CD quality. If you have 32 bits, it's like DVD quality, for example. Okay, so basically it depends on the, you know, the smaller the quantization, the closer you are to the actual values of the analog signal. Okay, so quantization takes an image, or basically let's talk about one-dimensional first. If you have something that looks like this, okay, assume that these lines, the lines of this page actually are the quantization levels. Okay, so for example, this is level 0, this is level 1, this is level 2, this is level 3, and this is level 4. Okay, if you have a signal that looks like this, basically what usually happens in quantization is that you use nearest neighbor interpolation. So basically, this will be here, 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 and this will be here, this will be here, this will be here the same way, this will be here, and so on. This will be here. Okay, if you have a point in the middle here, so basically the level between 1 and 2, all these will go here and all these will go there. So basically this part of the signal would look like this. And here the same exact thing. You'll have this here, okay, this. Okay, so basically since you don't have many levels, you're not able to capture the way the analog signal looks like. If you have a much larger number of levels, then you can express almost exactly the same value that the analog curve had. Okay, so it's exactly the same in images. Each image, as we said, that it's a matrix. Okay, so the value of each one of these points, okay, is quantized. Why quantized? Because actually anything on the computer has to be quantized. You cannot put an analog value inside the computer. Because what? Because basically an analog value or a real value has infinite number of bits, because actually it can take any value. So basically you have to quantize it. And depending on the level of quantization, the quality of the image will basically change depending on that. Okay? The thing we started talking about last time is that it's basically based on what we talked about here. Basically, you're mapping the range between the minimum let's just go here, the maximum, this range, okay? You're mapping that to another range, the quantized range. This is the after quantization, okay, between 0 and L minus 1, okay, where L equal to 2 to the power n, which is number of bits, number of quantization bits, okay? So basically you're mapping that to a discrete. This is analog, this is real numbers, this is discrete. Meaning that I have 0, 1, 2, 3, I don't have 0.1, don't have 1.4, I don't have 10.5, I have only integers. Okay, so this is the mapping that I would like to have. So the way I do the mapping, if I have any point in the middle here, I would like to map it here to a level. The way I do that is I get the difference between this point and the minimum and relate that to as a ratio to the whole range between maximum and minimum. This should be equal to the value that I would like to estimate minus 0 over the whole range, which is L. Okay, so basically the way I do it here is if I have a value is equal to x, I'll basically have x minimum over x maximum minus x minimum. Once I do that, the range of this variable here, or this transformation here, will be between 0 and 1. Why? Because if you are here, if you are at the minimum, then minimum minus minimum is 0, so basically it'll be 0. If you are at the maximum, then x maximum minus x minimum over x maximum over x minimum will be 1. So basically this has a range between 0 and 1. If I multiply that by the number of levels, okay, then I will have the range between 0 and L, but actually I would like to have it L minus 1. So that basically between 0 and L minus 1, it will be basically the L levels. Okay. After I multiply it here, it's going to be between 0 and L minus 1. But actually, it's going to be still real numbers. I would like to have these real numbers converted to integers. So basically, I use round after that. Okay, so that basically, if I have 10.5, it's going to be approximated to 11. If I have, for example, 11.1, it's going to be approximated to 11. Okay, so basically, let's try to do that. Okay, and let's try to see how the effect of different quantizations will affect our images. Okay, is the idea about interpolation quantization clear? Do you have any questions about quantization, the way we are going to do quantization?
I think it's clear for me.
Okay. Please, whatever I have in the lecture, please go over it, try to repeat it, try to understand it by yourself, try to look at the video of the lecture. If you have any questions at the beginning of next lecture, please, let's go over it again if you have any questions. So at the beginning of each lecture, I expect you to have questions to answer before we go into something new, okay? Now we're going to implement that for exactly the same image. You just continue on the same code here. Just add another section called quantization. Okay, and basically we're gonna start with, let's start with exactly the same two images. Okay, let's start with the black and white first, the grayscale image first, and then we try the same thing with the color image and see what happens. Okay, so first of all, what we need to do is compute maximum minimum. Can you please mute the audio, because I see I can hear some. Okay. Please mute audio unless you're having a question, please. Okay. Image minimum is equal to minimum. I would like to have minimum of the image. Okay. Minimum of this image. Okay. So if I say minimum of image, as we said last time, the minimum computes the minimum along the first dimension only. So if you have two dimensions, it's gonna basically give you the minimum of each one of the columns that you have. Okay, and we don't want that. We would like to have the overall minimum, the minimum of the whole image. So basically, in order for you to get all the elements, the minimum of all the images and all the points in the image, you just write it like this. If you write a two-dimensional array, a three-dimensional array, any multiple dimensional array, just a column, just a single column like this. So basically, you're selecting all the elements in the array. So this is the minimum of the array, and this is the maximum. Do it the same way. And then we're going to say that image Q, which is quantized image, will be equal to, let's just repeat exactly what we did before, image minus image minimum. And over image maximum minus image minimum. And this whole thing basically going to be between 0 and 1. So what I'm going to do is multiply it by the number of levels. Let's assume that number of bits of quantization is equal to, it's already 8, because the image is between 0 and 255. Let's just select 4, for example, okay? Then the number of levels will be what? Oh, let's just keep it number of bits so that we can see it like this. So I'm gonna multiply it here by 2 to the power n bits minus 1. Okay, so this is L minus 1. This is L here. okay? -1 because basically I would like to have a maximum. If I, for example, selected 16 levels, then I would like to have the maximum 15 because it's from 0 to 15, okay? These are 16 levels. So when I do that, I'm gonna come up with an image that has real values, okay? I don't like to have real values. I would like to have integer values. So basically I use round here, okay? There is a problem with this expression here. We're gonna get an image that has basically, if I use 16 levels here, 4 bits, the values basically will be like from 0 to 15. When I try to display them on the screen expects you to have numbers between 0 and 255. So when you have only values until 16 or 15, the image will look really dark. Let's see it ourselves. Okay, here. Let's have another figure. And we're going to use image show of image cube. Let's see both images actually, so that we can know the original image, how it looks like, and the quantized image, okay? So subplots 1, 2, 1 have 1 by 2 array. Actually, for the first one, I'm going to display the original image, so it's just image. And for the other one, I'm going to display the quantized image. As you see here, there's an image here actually that looks dark. It looks almost black. Because basically what we did here was that we did not scale the images to the scale of the display itself. So what we should do is basically I would like to restore the range of the display or the range of the image to the original range. Okay, it has 16 levels, but actually I would like to have these 16 levels mapped all the way between 0 and 255. So basically what I will do is multiply this by 256 over 2 to the power 10 bits. Let's see what that does. If I have here number of bits equal to 16, then basically I'm going to multiply my image by 256 over 16, which is 16. Okay? Which means that I'm going to have a maximum here. When I have 16 here, I'm going to have 256 in the output image. Let's see how that changes the display of the image. It's showing the image, but it's very poor. It looks very poor. Okay, let me try some other things. I'm not sure if this is gonna affect things, but actually let's just call image here double of that. There's a problem when we divide images that are integer, because sometimes you end up with either 0 or 1, which is a problem. Okay. You need to have image as double because when you divide it by a larger number, it's going to give you a fraction. Okay, when you multiply this fraction by a large number, then it becomes actually a large value again. But actually, if you have an integer, if you have 1 over 3, it's going to come up as 0. So let's try if this makes a difference. Actually, I don't see that it's. For some reason, it doesn't. Okay, let me try again. Instead of putting the double here, I'm going to put the double here in the image here. Oh, okay, we need to have it here. Actually, must have it here.
Please, doctor.
Yes, go ahead.
Why we use the quantization when we processing an image?
Because basically this is when you get an image, you get it as an analog image. Basically, you have to quantize it in order for you to store it on a computer. Without
Yeah.
quantization, you cannot store it.
But it's already quantized.
What?
It's already quantized or not? Or how?
Okay, sometimes, okay, if it's already quantized, then you might want to change the quantization if you want to save space. If you want to make the space a little bit smaller, instead of having each point stored in 4 bytes, for example, you want to store them in 2 bytes. Okay, and I'm going to show you now the image, how the quality of the images look like, and basically you realize that sometimes you can use very low quantization, very small number of bits, and the quality would actually still be very good.
Yes.
Okay, let me put that here. Let me try. Actually, you have to, in order for you to get the minimum and the maximum correctly, you have to have double of image here. And you use double here also as well. Let's try and see if that makes a difference. This doesn't look right. Okay. Let's see here, 256 over 2 to the number of, okay, maybe you can, but it shouldn't really be a problem. To the power k, that shouldn't be a problem. To the power number of bits. Okay, let's try it again. Okay, let's just check on the image Q. It's double. Okay, it shouldn't be double. I'm not sure why it's double actually. Here we multiply by an integer here. Should multiply by an integer here. Still the same problem. Here image Q still double. I'm not sure why it's still double. Oh, okay, sorry, round. Round might not actually yield some, maybe you can look at the image Q itself and see how it looks like as numbers. Actually, it doesn't look double, like double. It looks okay. I'm not sure why actually it's very bright. It doesn't have many zeros, which is a little bit strange. It has 80, it has, okay, let's try it again, see what's happening here. Double, let's just change that and see if this affects anything. Let's just have it as 5. Still has a problem here. Okay. Maximum, minimum. Okay. Times due to the number of bits. Let's keep it like this and see. I'm very surprised actually because it looks a little bit strange here. Let me try something bigger. Actually, it looks okay here. Kind of looks okay here. I'm not sure why it's not displaying properly. Let me try and show. Image show has a problem here for some reason. Okay, maybe I can let me try make it integers. Okay, is integer or right? unt8. Unt8 is okay. So let's try to display unt8 of MHQ. Yes, it's working. Actually, there's a problem in image show that has problems when you use a double. It's exactly the same array, but actually it's in a double format. So what I'm going to do here is just keep everything the same, and basically MHQ here will be just uinteger 8 of this whole thing. Let's try it here. Okay, see here. Actually, this is okay. This looks kind of okay. It's not really, you don't really see many differences between these two. But if you try to use a lower position, like 4, let's just try 3. Just see. So you have only 8 levels, okay? See now the 8 levels. Do you see the difference between these two images? See here? The very small variations here become really coarse because you have only 8 levels. So basically you're jumping between levels, okay? So as if basically instead of having steps 0, 1, 2, 3, and so on, what you're going to have here is 0, 8, 16, and so on. So basically the middle levels that actually make the image look very smooth when you have a gradient in the image, they are not there anymore. So when you make the number of quantization levels smaller, then you will end up with something that looks like this. Just take it to the extreme. Let's just go with 2 and then 1. 1 will make the image as binary image. See now how it looks like? These are 4 levels. Basically, it's exactly the same image. This is the original image. This is the image with a number of levels of 2 to the power 2, which is 4. Okay, looks really bad actually. Many of the details that are in the middle basically are gone. Let's try that with 1. 1 means that I have 2 levels, 2 to the power 1, which is 1 level. How do you like that? Almost unrecognizable. Okay. The thing is, I wanted to bring to your attention, if I take 6, for example, okay? Can you see the differences between these two? Actually, it's very difficult to see differences, actually. There are differences, but actually you have to be really, you have to basically look closely to see differences between these two. So one of the things that I'm going to ask you, or basically that you will go into a report in your research problem 1, is to take one image and try different quantization levels and let me know when you think that this quantization level is sufficient. Okay, from your point of view, from what you're seeing from the images. Different images have different character. Some images actually you can feel right away when you have only 1 bit decrease of quantization. Some others actually you can basically make the quantization half. Okay, instead of having 256, you can have 128 and it will be just fine. Here actually we're talking about 64 quantization levels. Okay, so basically it looks okay to me actually. Let's try that with the color image. Do you have any questions first about that? Do you have any questions? Do you see the difference I'm talking about? So
yes,
basically, okay, what we talked about in the magnification and the rotation was geometrical problems, or basically the errors that come from geometry, from basically expanding the geometry of making or having to estimate new points. The quantization is a little bit different. It's basically, it's in the representation of each point. So we're talking in the quantization, we're not talking about the image, we're talking about the pixel itself. How many points or how many bits we use to represent each one of the points in the image. And this makes a big difference. Okay, so let's try that with the color image and basically conclude for today. Okay, let's see if the code will stand. Actually, this would work. It shouldn't be a problem. Just remember that when we have a color image, what we're going to have here is like X and Y, like for example, 100 by 100 by 3 when you have color. Okay, when you have black and white, it's just going to be 100 by 100. So I'm not sure if it's going to make any difference. It shouldn't make any difference actually, because we're using image as it is. We didn't really use the third dimension, so it should work. Let's try it like this and see if it works. It looks okay. Actually, I don't see many differences between these two. Let's try it with a smaller number of quantization levels. By the way, some people, when they are writing code, sometimes they have to perfect the code before they try. Actually, it's a good thing to try. If you're not sure about something, try it and see if it works or not. So I'll try here with 4 bits. So basically, I'm talking about quantizing the image into 16 levels. Do you see differences? Actually, it's still okay. Yeah, it's still not bad. Do you see any differences?
Like the same, both of them.
The what?
I don't see any.
Yes, I don't see many differences actually. Let's go down to 3. Actually, still okay, but actually you might see some differences. See here? Let me magnify it. See here?
Yeah, there's a difference.
You started seeing the gradient becomes a little bit coarse. See here? So instead of having a very smooth gradient like here, you have basically you have to have steps, larger steps. So you would end up with images that has batches like this, because the gray levels, as we just showed actually in the explanation here, when you have coarse levels like this, then all these points here will become one level like this here. All these points here will become one level here. So basically, you're going to end up with batches in the image. Look like a batchy, basically, image with areas that are not really, whenever you have a gradient, you don't really see a gradient, you see a step, okay? So basically, this is not suitable, okay? Let's try that with even 2. This is very clear now, okay? See that here, without even trying to magnify to see what's going on, it's very clear, okay? See this area here, this area here, you have so many details here that we're lost here, okay? So the quantization actually affects both grayscale and color images the same way, okay? And the only way to realize which quantization level is more suitable or can be suitable for the images, basically try it yourself. Basically for the color image, as you saw, we didn't really realize basically the same levels that were causing problems in the grayscale were actually okay here when we started. The first image that the first quantization level that we use. So basically you have to try the image to realize whether the quantization level you're talking about is suitable or not. Okay, and this is gonna be like a part of the experimentation you're gonna be doing. Okay, in this course, actually, I would like you to experiment with things. So basically, try different images. Try and basically try to form an opinion about something. Form an opinion about the quality of the image. Okay, and justify it by what you see. Okay. So it's a very important part for you to try the same code. The code I'm giving you is like a starter code. You can try this code, you can basically modify it, like use different magnification, different rotation angle, different quantization level, and try different images. Instead of just using the images, the sample images that are available from Matlab, you can download images. Just look for MRI images, look for ultrasound images, look for different kinds of images, and try them and see whether you have differences in different types or not. Okay, so a good part of your learning will be basically through experimentation. Do you have any questions? Okay, if you don't have any questions, this will be it for today. I'm going to post the code. I'm going to post the notes, that the handwritten notes that I put here. And I'm not sure if you saw the ones from last time, but actually I posted them. If you need any help, if you try to run the code and run into problems, please don't wait until next time. You can send me an email and I'll reply to you. Okay, so that you you get started right away. Okay.
Okay.
So, any question before we conclude?
For me, it's okay.
Okay. Okay, thank you, and inshallah, see you again on Wednesday, inshallah. Okay.
Thank you very much.
I have one question before we conclude. We have the Wednesday after next. It's going to be the Al-Yawm Al-Watani, National Day. Would you like to continue on the National Day, or if you have I know that many people actually travel during the National Day, or because actually it's going to be a long holiday, because you're going to have Wednesday, Thursday, Friday, and Saturday. So if you don't want to have today, please let me know. Okay, if you don't want to have a lecture on the Wednesday, the 23rd. Okay.
I think okay, we can continue with the National Day.
You have a feedback, but let me know next time. Okay, at least you know your basically what your plans are, and basically we can talk about it next time, inshallah. Okay, so next time we're going to decide whether we're going to have a lecture on the 23rd or not. It's fine with me, because basically for graduate courses we don't have to finish at a certain time. We can have that extra week because we're not going to have exams. Basically you're going to have a project, and basically the project will be take home, so you don't have to finish at exactly the last day of classes. So if you need that week, we can replace it later if you want to take the vacation, the holiday. Okay, so next time inshallah we'll talk about that, and you let me know exactly what you want to do. Okay, please, if you have any questions about what we talked about today, at the beginning of next lecture, inshallah, please let me know your questions, and we'll continue with the other things in this part of the course after that. Okay, I don't have any problems in repeating things. Okay, the most important thing is to learn, to basically learn what we are talking about so that you can use it. Okay, it's not just this is not theoretical, this is practical. You have to be able to take whatever we're talking about here and apply it yourself. If you had any problems, even if it's a problem that is particular to you, like you have a particular problem in Matlab, please let me know and I will help you personally. Okay, so
Okay,
good luck inshallah, and I'll post the material inshallah today. The recording of the lecture is usually available after, as I was told from the college, that they take about 6 hours to make it available. So basically by tomorrow morning, inshallah, the recording should be available to you if you want to. Okay?
Okay.
Good luck inshallah. See you next time inshallah. Assalamu alaikum.
See you. Morning.